Let's construct the tensor product. Okay, so we'll show the existence by explicitly constructing the tensor product of two given modules m and n. Okay, so recall starting point again. I need to have m comma n, two abelian groups or z modules. Now, what was a tensor product? The tensor product was a pair t comma alpha. Now, what is t? It was a map from m cross n, where t is t is a z module and alpha is a map from m cross n to t. So, t is a z module and alpha is a map which is z bilinear. Okay, we need this such that there is a certain universal property which is satisfied relative to if you take another such pair p comma f, then there is a map from t to p which makes that diagram commute. Okay, so that was the definition, but let's start out by trying to construct this z module t. Okay, so there are a couple of steps involved in this construction. The first step involves the free module that we talked about. So let's do the following. Let's define the set S to be m cross n. Okay, think of it as a set. Think of this only as a set. No additional structure. Okay, ignore the fact that there is an addition operation on m, there is an addition on n and so on. Forget all that. Just think of it as a arbitrary set. Okay, and let's define f to be the free abelian group or free z module. So let this be the free z module on this set S. Okay, in fact, if you recall, the free z module was actually a pair. Okay, f comma gamma. So how did we define the free module? Well, it was, what was gamma? Gamma is just a map of sets from S to F, just an arbitrary set function, such that there was a certain universal property with respect to such pairs. Given any other group and a map from the set S to that group, any other Z module, any other abelian group, then there is a map from F to that group. Okay, so that's what we looked at last time. So what we'll do is we'll just take the free Z module on S. Look at this map gamma. Now, in fact, we constructed the free module explicitly. So recall what is the free module. Therefore, what do the elements of F look like? Recall that we constructed F as the set of all functions of finite support on S. So this was all, you could think of it as functions from S to the integers such that H vanishes outside a finite set. Right, and but on the other hand, we also wrote it in terms of, so we said every element of S has in fact a unique expression as follows. So you can write it as, so in this case the set S is all ordered pairs m comma n. So let me denote it like this, where m comma n ranges over the set S in this case, which is m cross n. Okay, where the C is Cmn, so we should say such that Cmn is an integer and finitely many are non-zero. So only finitely many non-zero. We should say all but finitely many are 0. Okay, so this was the construction of the free module, and this map gamma that we constructed. So given a set S, there is this map to the free module on S, which is the following. Take any element S, in this case the element m comma n of S, you map it to the corresponding indicator function Emn. Okay, or think of it like a basis vector if you wish. It's 1 only on Mn and 0 everywhere else. So this was the map gamma. Okay, so first step, we construct the free module on the set S. Okay, now step 2 in the construction involves the other thing we looked at last time, the other construction, which is that of a quotient group. Okay, so consider the following elements of the free module. Okay, consider the following elements. Okay, what are these? They are elements of the following form. So let's look at E m1 plus m2 comma n. So this is an element of F. Now F is an abelian group, so I can look at this subtraction. So it's a Z module, so I can look at this element. So this is some element of S. So consider the following elements of F, sorry. So this is an element of F. So take all these elements where m1, m2 come from M, n comes from N. Okay. Union, the same sort of elements in the other component. Okay, now M comes from M, N1, N2 come from N. Okay, so I've constructed a collection of elements, and what I'll do is I will take the subgroup of F generated by these elements. Okay, so let H denote the subgroup of F generated by these elements, which means it's the smallest subgroup which contains these elements. Okay, generated by these elements. Okay, i.e. H is, well, what's it? It's the intersection of all subgroups H prime, where H prime is a subgroup of F and H prime contains this collection of elements. Okay, so maybe we should call these elements something. So we call this the set U, and H should contain this set U. H prime should contain U. So it's the intersection of all such subgroups H prime. So I should say H prime is a subgroup. Okay, now of course here everything is an abelian group. F is abelian, and so any subgroup is automatically normal. So what we can do is look at the quotient group. So we'll look at the following: take F and look at F mod H, that's the quotient, and there is a projection map. So what is this? Given any element of F, you just look at its coset. So here everything is written additively, right? It's an abelian group. So instead of writing it as GH, instead of the multiplicative notation, I will just switch to the additive notation. Okay, so I will call this coset as G plus H. So which is what you usually write as G bar, the coset of G. So this is of course a group homomorphism. Now let's sort of put these two things together in step 3. So what have we done so far? On the one hand, from M cross N, thought of as a set, I've got a map, a set map to the free group. Now from the free group, I have a group homomorphism. So pi, remember, is of course a group homomorphism to F mod H. Okay, now I'll call this as T. Okay, this is going to be our tensor product. So this is my definition, that this is the Z module T. So observe, so let's define T to be just the abelian group F mod H. So it's an abelian group, in other words it's a Z module, and I need to define a map, right? In order to say that this is the tensor product, I need to construct a map from M cross N to T. The map is just the composition of these two maps. Okay, so I will call this composition as alpha. So what is alpha? It just denotes the composition of pi and this map gamma. So our claim now is going to be that T comma alpha is a tensor product of M and N. Okay, so I say a tensor product, but recall we already showed that if it exists, the tensor product is unique up to a unique isomorphism. But we need to first show that this satisfies the axioms or the universal property of a tensor product. So let's first check what do we need. T is a Z module is all right, but we need to check that alpha is a bilinear map. So let's verify our claim. Okay, so here's the proof of the claim. First thing we need to check is that alpha is in fact bilinear. Okay, so what is alpha? It's a map from M cross N to T. Okay, now alpha is just pi composition gamma, and it's sort of strange because gamma is just a map of sets. Pi is a group homomorphism, but we're claiming that at the end, after you compose these two, this alpha has this property of bilinearity in the two variables. Okay, so let's check that this is true. So what does bilinearity require us to check? We need to take m1 plus m2 in the first component, n in the second component, and let's see what that goes to. According to this definition, this is pi of gamma of this, which is just, well, gamma of this is just the element e m1 plus m2 comma n, and pi is just mapping it to its coset modulo h. Okay. On the other hand, we need to check whether this is the same as alpha m1 plus n, sorry, m1n plus alpha m2n. Okay, we need these two things to be equal. So the question is, are these the same? Okay, so let's verify. So I will compute the other side. This, by the same token, is E m1n bar, this coset, plus E m2n bar. Okay, now what do these cosets really mean? Cosets, of course, mean that I look at this plus h, right? So the question is, when are these two equal? Are these equal? How do I check? Okay, now how do you check that two cosets are the same? So suppose I give you a coset g1 plus h, okay, and I need to check whether this is the same as g2 plus h. Then recall that this is just the same as saying, well, I'll use again the subtraction here instead of inverse. G1 minus G2 belongs to H. Right? This is exactly what it means for two cosets to be the same. So here we just check similarly. So the addition, by the way, so when I say E bar of this plus E bar of this, I am trying to add two cosets, but recall that is just the same as, so let's also simplify this a little bit more. This is nothing but, so how do you add two cosets? So for example, what is G1 plus H plus G2 plus H? What's the addition operation on the coset space? On the quotient, it's just you add the representatives. Okay, so here again I do the same thing. I get E m1n plus E m2n. This is an element of F, and I take its coset modulo H. Okay, so let's check that these two answers are the same. Okay, I claim that they are in fact the same. This is the claim. Okay, so let's check. So to check it, I need to take that difference and check that the answer is in H. Okay, so let's compute what's the difference of the two representatives. So this again is actually this plus H. Okay, so let's write out the two expressions. On the one hand, it's this. Okay, and I need to subtract from it whatever is on the other side, E m1n minus E m2n. Okay, and I need to check whether this element is in H, but recall this is exactly one of the generators of H, right? I mean, that's the reason why H was chosen in this particular way. This was, of course, this is definitely in H because it was one of the generators of H. Okay, so similarly the other one. So this is done. So the claim is true. So in other words, the first bilinearity in the bilinearity in the first variable is in fact true. That is, this equality holds. Okay, we have proved this, but the same sort of argument with the second component is also true, because that's the other generator of H, the other kind of generator. So this is the same as. Okay, same proof. Okay, good. So we have shown that alpha is bilinear, but what's the second thing we need to do? We need to check whether this pair T comma alpha has the universal property of a tensor product. Okay, let's check the universal property. So what do we need to do? We need to start with some pair P comma F. Okay, given PF, P is a Z module. And what is F? F is a map from M cross N to P, which is bilinear. Okay, F should be a bilinear map, Z bilinear. Okay, given these two, I claim that we can do the following. We can construct. So what do I want to do? I want to construct a map from T to P, right? I want to construct a a Z module homomorphism, Z linear map F tilde, such that this diagram commutes. That is, F tilde composition alpha gives me F. And this should be unique also. So there exists F tilde and this is unique. Okay, so this notation here just means unique. There exists with an exclamation just means there exists a unique whatever it is that we want to say. Okay, so the uniqueness is denoted by the exclamation. Okay, good. So let's show that this is in fact true. For this, we need to go back to the definition of T. So recall T was constructed in 2 steps. So we'll also construct this map via those intermediate steps. Okay, so let me do this. So on the one hand, I have a map from M cross N to P. Okay, F is actually Z bilinear, but for a start, F is, think of F only as a map of sets. Okay, why do I want to do that? Because the very first step in the construction of the tensor product involved using the free module. Okay, so before I bring in T, let me first do F. Okay, now look at this diagram. F is Z bilinear, but at the moment let me not worry about that. F is just a set map. I will only think of it like that. Okay, I'll come back to the Z bilinearity. So it's a set map. Therefore, by the universal property for free modules, I know that there exists a unique map from F to P. Okay, so this is a unique map. So maybe we should call it F, maybe something else, so as not to confuse with the tilde there. Let me call it F bar. Okay, so there exists a unique map F bar. Maybe we'll just call it G. There's a unique map G. What sort of map is this? This is a map of, it's a homomorphism of groups. There exists a unique Z linear map G from F to P such that the diagram commutes. Okay, what have I used here? Just the universal property of the free group. So this is the universal property or the definition, if you wish, of the free group F comma gamma, the free abelian group or free Z module. Okay, now step 2, we will use the universal property of the quotient. Now recall F mod H is what is T. This is a projection map. Okay, now forget about the top part of the diagram. Let's only focus our attention on just this portion. So I have this map. Just look at the arrows in red. Okay, I have the arrow pi and I have the arrow G. And what was the universal property of the quotient F mod H? If I have a group homomorphism from F to P, whose kernel contains H, okay, then I know that there exists a unique map from F mod H to P. Okay, so now step 2 is, if the kernel of G contains H, then we know the following. Then there exists a unique map, maybe which we'll now call G tilde. It's a unique group homomorphism. So in this case, it's everything is an abelian group. So I can think of it as a Z module morphism. There is a Z linear map G tilde from F mod H to P such that this diagram commutes, meaning the diagram in red, G tilde composition pi gives me G. Okay, this was by the universal property of, so this last bit is the universal property of the quotient group. Okay, now let me show that I claim that the kernel of G certainly contains H. Okay, now how do I prove this? Now that's where I need to go back and use the fact that it was, F was not just an arbitrary set map, it was actually more than that. Okay, of course, if it's a Z bilinear map, in particular it's a set map, but I'm going to use the Z bilinearity to show that the kernel of this map G contains this subgroup H. Okay, so the claim is this is true. Okay, so let's prove this. So claim kernel of G is certainly contains H. Okay, so H is inside the kernel of G. Remember, however, to prove this, H is generated by a bunch of generators, right? If I show that the generators are all there inside kernel of G, then it automatically follows that H itself is inside the kernel of G. Okay? Because the kernel is a subgroup and H is the intersection of all subgroups which contain that collection of generators. So proof enough to show that the generators belong, enough to show that the generators, which I call U, is contained in kernel of G. Okay, now let's prove this. So what's a typical element of U? So let's show it for one kind of element. So look at E m1 plus m2 comma n minus E so this is a typical element of U, and let's show that it's inside the kernel of G. In other words, if I apply G to this, I will get 0. Okay. Now how do I do this? Well, observe that. So what do we know about G? G composition gamma is F. Right. Now, what are these E's? They are just gammas. So, if you see, what is this map? This is just gamma evaluated on the ordered pair M1 plus M2. Okay, minus gamma of, just by definition. What does gamma do? It just maps an ordered pair to E of that ordered pair. Okay, now G is however a group homomorphism. So I know that G is Z linear. So this splits into 3 pieces. So this is G of gamma of. Okay, since G is a group homomorphism, since G is Z linear. Okay, but now observe G composition gamma, which is what I have here. This is exactly F. That was the defining property of G, right? It makes this diagram commute. So G composition gamma was F. So I will replace all the G gammas by F's. So this is nothing but F of M1 plus M2 comma N. But then that's 0 because F is bilinear, because F was bilinear. Okay, so what this implies then, so we have showed that this generator belongs to the kernel. Similarly, you can show the other generator. Okay, so similarly, similar argument shows that the other generator E m comma n1 plus n2 is also in the kernel of G. Okay, so we have managed to show this, that all the generators belong to kernel G, and as I said before, if the generators belong, then the subgroup they generate definitely also is a subset of the kernel. Okay, and now therefore we are done. Therefore, by the universal property of quotients, what does it imply? It implies that there exists a unique map. So, we have shown that kernel of G contains H. This is true. Therefore, there exists a unique Z linear map which makes this diagram commute. Okay, good. So what we have finally established is that this the existence of all these maps. So let's just copy this. So we have shown now that, okay, so we have constructed, starting from F, we constructed this map G by using the universal property of the free abelian group. Then starting with G, we constructed G tilde by using the universal property of quotients. Okay, and now this is going to be our final map. So the claim is that G tilde is what we need. So I mean, that's what we called as F tilde. So we take F tilde to be this final map G tilde. So take F tilde to be this map G tilde. Okay, so I mean, F tilde is what we needed to construct. Okay, so let's just show that this makes the overall diagram commute. So what's the property we needed? So I'm going to find this as my map F tilde. Okay, so now I need to check that F tilde, so need to check finally that F tilde composition alpha is equal to F, right? So that was the that's the thing we need to do. So at the moment, let's get rid of all the intermediate steps. So this is the big diagram we are looking at, and the map alpha is just this overall map. The composition of these two maps is what we are calling alpha. Okay, and our claim is that, so this was called F tilde, this map. So F tilde composition alpha is F. That was the universal property of the tensor product that we need to establish. Now why is this true? Well, because each of the two smaller diagrams commute. Okay, so how do we prove this? So let's put all these back. Okay, so now let's observe to prove this that so first this upper triangle commutes. So proof, let's just do it. So first observe that G composition gamma is equal to F. That's the upper triangle commuting. Now the bottom triangle commutes, so which means G tilde composition pi is G. Okay, now I will substitute for G into the top equation. So this means that G tilde composition pi composition gamma is equal to F. But pi composition gamma is exactly our alpha. That was our definition. So G tilde composition alpha is exactly F. So that's exactly what we need to prove, right? I mean, we are calling F tilde as G tilde. So this is done. So what has this done? It has shown that the pair, therefore the pair T comma alpha certainly has the first issue, I mean the first property, that there exists a map from T to the module P. Okay, but further we need to show that this map is unique, right? So that's the last remaining bit of the definition. So we have shown that from M cross N alpha, given any pair PF, there exists a unique, I mean there exists a map, F tilde is all right. Okay, there exists F tilde such that F tilde composition alpha is F. That we have shown. Okay, but why is such an F tilde unique? That's the last bit. Okay, so let's show uniqueness. So suppose I have another map. Okay, so let's call this H tilde maybe. So if I have another map, Z linear map H tilde from T to P, such that the diagram again commutes. Okay, so suppose there exists a map H tilde from T to P, Z linear map is also F. Okay. Now observe, what does this mean? This means that both F tilde and, so this is alpha of Mn is F of Mn, but that's the same as H tilde of alpha of Mn for all ordered pairs Mn. So what this means is that F tilde and H tilde, so if you look at this, F tilde and H tilde, they agree on the elements of the form alpha of Mn. Okay, so this means they are equal to each other. Therefore, F tilde and H tilde agree with each other, have the same values on the image of this map alpha, right? That's what this means. Any element which is in the range of alpha or the image of alpha, on such elements F tilde and H tilde take the same value because it's F of Mn. Okay, but the claim is that this image of alpha generates this group T. Okay, so that's the last claim we'll make, that this image of this map alpha generates the abelian group T. Okay, so once this claim is proved, then it implies that F tilde and H tilde agree on all of T. Okay, so observe that once claim is proved, so assuming the claim we are done, so we will just write that as an aside, assuming claim, what do we obtain? We can conclude that if two homomorphisms agree on a generating set, then they agree everywhere. And then F tilde agrees with H tilde on all of T. Okay, so let me leave this as an exercise for you to prove. that if two group homomorphisms agree on a generating set, then they agree on the entire group. Right, okay. So let's prove finally the claim. That's all remains, that the image of alpha generates the module, the group T, and that again is just from the definition. So what was alpha? How was it defined? You first take this map gamma to the free group. So each m comma n goes to E sub mn. Okay. Now observe that the E sub mn's, they generate F for sure. Okay, this we know. E sub mn's, in other words, the image of gamma. Okay, this is just the image of gamma, that certainly generates the free module or the free abelian group, right? Why is that? Because, well, we already showed this. Every element of F can be written as a linear combination with integer coefficients of the EMNs. So if you have EMNs in some subgroup, then that subgroup is the entire group F. Okay? It's the entire module F. Now, okay, good. So they generate F, and now this map pi here is a surjection. So this is F mod H, which is T. Okay. So since pi is an onto map, and this is a generating set, it implies if you apply pi to this generating set, then that's again a generating set. This generates F mod H since pi is an onto map. Okay, again exercise, this is just a completely general fact. If I have two groups and I have an onto map between them, which I will indicate by this double arrow, so I have an onto homomorphism, we will call it phi. Then if a certain subset generates G1, so if S subset of G1, then S generates the group G1, meaning the smaller subgroup of G1 containing S is just G1 itself, then its image generates G2. Okay, so just a straightforward exercise using the definition of what it means to generate. So when I have an onto map and I have a collection of generators for the domain group, then their images will generate the image. So this is now, this goes to EMN bar. Okay, so therefore because pi is onto, this means that the EMN bars. So in other words, i.e. what we are saying is that you take these elements EMN bars inside T, they generate T. Okay, so this collection of elements. Okay, and therefore we are done. So that's the last claim we needed to prove, because this is exactly the image of alpha. Okay, so therefore this shows that this map is unique. So we have constructed the tensor product because we have shown that it has the universal property, that there exists a map F tilde that we needed, but not only that, that map F tilde is unique. Okay, good. So therefore conclusion finally, therefore final conclusion, T comma alpha is indeed a tensor product as claimed. Okay, now we have so a couple of remarks on notation, which is that these, so we tend to write T as M tensor N. Okay, so this module T that we have constructed, or in general any tensor product if you wish, can be denoted as M tensor N over Z. Okay, the Z is just to say they are both Z modules, and we are thinking of the tensor product as Z modules. Now this alpha also has a notation. So the alpha, recall, is a map from M cross N to T, right? So T, which I am now calling as M tensor N over Z. Right now sorry, it's alpha. So any M comma N goes to what we call EMN bar, right? Now this image we denote it by m small m tensor small n. Okay, so this is again notation. So this is notation for, so T is called m tensor n, and this maybe I should write this the other way around. So this E m n bar, so this alpha of m comma n is also denoted like this. You take little m tensor little n. So that symbol will just denote the element alpha of m comma n. Okay, and so what do we know finally in terms of this new notation? What we mean is that so what we know is this. So alpha is bilinear. That in this new notation just says this: if I take m1 plus m2 tensor n, that's just m1 tensor n. So recall this notation just says it's alpha, right, of m1n plus alpha of m2n. And similarly the other m tensor n1 plus n2, which means alpha applied to this pair, okay, where m's are in m and n's are all in capital N. Okay, and the other fact that we just said, that the EMN bars generate the tensor product. That was the other fact. What it means in this notation is the following. So recall, this is just saying that any element of T can be written as a linear combination with integer coefficients of the EMN bars, right? So this is therefore saying any element of m tensor n, this module, which is T, can be written as follows: as well as a linear combination with integer coefficients, if you wish, some finite sum, as a finite of terms like this. Okay, so this is a finite sum, it ranges over some finite collection where mi's are in m, ni's are in n. Okay, why is this? Well, recall, we know that we can certainly write it as a linear combination CMN in our earlier notation. CMN, EMNs are a typical element of F, and this is now when you apply the map pi, this gives you an element of T. Okay, but this I will rewrite in my in this other notation. So this is nothing but summation CMN alpha mn, if you wish. I mean, this is a finite sum over certain m's and n's. So what I am doing here is just calling the m's and n's which appear in this summation as mi and ni, but this coefficient c that I get, this constant here, that I am just going to take into the so recall alpha is bilinear, which means that you also have this. So recall, by the way, when we said bilinear, so we also made this remark earlier, that this also means that if I take am tensor n, where a is an integer, then this is just a times m tensor n for all a integers, and this is also the same as m tensor an. Okay, why is this? Well, we proved this, that bilinearity just means that you can, multiplication by a is like repeated addition those many times. So this last axiom just follows from the other earlier ones. Okay, so this is, I can write this as alpha times, I can push this CMN, this number, into the alpha because of bilinearity, and now this final expression is what I have written in this way. Okay, so this is like saying, so this is my, this is one of my mi, I mean this is my mi and this is my ni. Okay, and so what we have finally shown is that any typical element of m tensor n can always be written as a linear combination of the various EMNs, and I can, often in terms of, when one wants to write down proofs and so on, it's easier to just choose this more compact way of saying it instead of putting some constant CMN in front. Okay, good.